Welcome, deep divers. You know how we love to take a complex topic, grab a stack of sources, and really dig in to find those surprising facts and those real aha moments. Well, today we're definitely doing that. We're blasting off, you could say, into the incredible, pretty explosive, and often really surprising history of rockets. We've got a fantastic deep dive lined up, pulling from some detailed historical accounts, including some really fascinating encyclopedic insights. Our mission really is to uncover the hidden origins of rocket technology, trace how it spread across the globe, and see how these amazing machines evolved. From simple fire arrows, believe it or not, to the powerful vehicles that eventually launched us into space and, beyond.
Yeah, and what's so fascinating, I think, is how the basic principles of rocketry, the things we often think of as like a modern invention, actually go back much, much further than most people realize. It really hints at this incredible ingenuity across completely different cultures and times, well before gunpowder even enters the picture.
Okay, so let's unpack that. If we're talking before gunpowder, what were these earliest hints, these sort of proto-rockets?
That's a great way to put it, proto-rockets.
Yeah.
The key concept here isn't, a tube filled with propellant yet. It's the fundamental principle. Action-reaction.
Newton's third law, basically.
Exactly. Push something one way, it gets pushed back the other way, and we see people grappling with this idea way back. Around 400 BC, you have Archytas, a Greek Pythagorean philosopher. He apparently propelled this wooden bird along some suspended wires using steam. It just went in circles around a pole, but it demonstrated the principle. Steam out, bird moves.
Right. And then fast forward about 300 years, Hero of Alexandria.
Yes, Hero created the aeolipile. You often hear it called the first steam engine, though it didn't really do work in that sense. It was this sphere sitting on a water basin. You heat it up, and steam shoots out of these little bent tubes, making the whole thing spin.
Ah, okay. So it's showing that expelling gas creates motion, a very direct demo.
Precisely. It's the core idea, just waiting for a more powerful propellant than steam.
So if those ancient devices sort of laid the conceptual groundwork, where does the real gunpowder rocket first ignite? Where does that story begin?
Okay, now we make a big jump. And the story takes us straight to China. This is where it gets really interesting and a bit debated too. The exact dating, well, it's tricky. Some accounts point to people like Feng Zisheng in 969 AD, or maybe Tang Fu around 1000 AD, inventing the gunpowder-propelled fire arrow.
But there's some pushback on those early dates.
There is. Some scholars argue that the specific type of gunpowder you need for propulsion, not just explosions, wasn't really refined until maybe the 12th century. So could rockets have existed before then? It's a question.
Okay, but by the 13th century, the evidence gets pretty solid.
Well, absolutely. Undeniable. You have reports from 1232 describing not just fire arrows, but these iron pots. Apparently when they exploded, you could hear them for 5 leagues, it's like 15 miles, and they caused devastation from shrapnel over a radius of maybe 600 meters. That's huge.
Wow. And there's something called a flying fire lance.
Yes, used by the Jin dynasty. And the interesting thing there is they had reusable barrels. So they weren't just one-shot devices. Shows some early tactical development.
And it wasn't just warfare, was it?
Not at all. We see the Song Navy using rockets in a military exercise in 1245, but then in 1264, there's mention of a ground rat firework. Apparently, it was used specifically to frighten the Empress Mother Gongsheng. So right from the start, you see this dual use, military power, and, well, entertainment or psychological effect.
And the thinking got pretty advanced quite quickly, didn't it? That Fire Drake manual.
The Hulongjing, yeah, mid-14th century. It mentions the first known multi-stage rocket, the Fire Dragon issuing from the water.
Multi-stage. That early. That's incredible.
It is. Thought to be used by the Chinese Navy. It shows they weren't just thinking about simple propulsion, but complex engineering concepts, centuries before they became common.
And they even had launchers, like multiple rockets at once.
They did. By 1380, the Ming Army was ordering things called wasp nests, basically rocket launchers designed to fire volleys.
Okay, so China is clearly the epicenter of this gunpowder rocket revolution. But how does this powerful new technology start spreading out?
Well, a lot of the thinking points towards the Mongol invasions in the mid-13th century. They were very effective at adopting and spreading technologies they encountered. They definitely picked up the Chinese fire arrow, and they even employed Chinese rocketry experts as mercenaries. There are reports of rocket-like weapons being used as far west as the Battle of Mohi in Hungary in 1241.
Wow, all the way to Hungary. So through the Mongols, it reaches the Middle East.
Seems likely. And then you get figures like Hassan al-Rama between 1270 and 1280. He wrote this incredible book. It had 107 gunpowder recipes, and 22 of those were specifically for rockets. And our sources suggest his recipes were actually more explosive than what was being used in China then. So they weren't just copying, they were innovating.
And the language itself tells a story here, doesn't it?
It really does. It's quite telling. In Arabic, saltpeter, the key ingredient, was called Chinese snow. Rockets were Chinese arrows. Fireworks were Chinese flowers.
And the Iranians?
They're called saltpeter, Chinese salt. I mean, it leaves very little doubt about where the technology was seen as originating. It's strong linguistic evidence.
Okay, so Middle East, check. What about India?
India's fascinating too. Handheld rockets show up there as early as 1300. But the big leap comes later. By the 16th century, the Mughal Empire under Akbar is using metal-cased rockets, iron casings.
Ah, so stronger than bamboo or paper. More reliable.
Exactly, more weatherproof, more powerful. And this really sets the stage for probably the most famous pre-modern rockets, the Mysorean rockets.
Right, Tipu Sultan. Late 18th century.
That's the one.
Yeah.
The Kingdom of Mysore, especially under Tipu Sultan, used these advanced iron-cased rockets really effectively against the British East India Company. They had a range of up to 2 kilometers, which was significant then.
And this had a direct impact back in Europe.
A huge impact. The British were so impressed and frankly terrified by these Mysorean rockets that it directly inspired William Congreve to develop his own versions back in Britain.
So the famous Congreve rocket owes a debt to India.
Absolutely. And it wasn't just Mysore. The Marathas also used similar iron-encased rockets around that time.
Okay, so India's innovating. What about Korea?
Korea jumped in relatively early, too. The Joseon Kingdom was making gunpowder by 1374, had cannons and rockets just a few years later by 1377. And eventually, by 1451, they developed the Munjang Hwacha. This thing was incredible. A mobile cart that could launch a whole barrage of rockets at once. Very sophisticated.
A medieval multiple rocket launcher.
Pretty much. Meanwhile, over in Europe, things were a bit slower on the uptake, maybe. Roger Bacon mentions gunpowder around 1267, but rockets don't clearly appear in warfare accounts until maybe the Battle of Chioggia in 1380, and even that's debated.
But they were thinking about improvements.
Yes, conceptually. Jean Froissart, around 1400, had this idea. He thought about launching rockets through tubes to make them more accurate.
Like a bazooka, basically. A forerunner.
Exactly, a clear ancestor of the modern RPG. Very forward-thinking.
And the word itself, rocket, where does that come in?
Oh, that's a fun one. It comes from Italian, rocetta. It means bobbin or little spindle, apparently because the early paper or cardboard tubes resembled weaving bobbins.
Huh, okay.
It got adopted into German around the mid-16th century and then into English around 1610.
So the 16th and 17th centuries in Europe, more innovation happening then.
Definitely. You get some really visionary thinkers.
Yeah.
Conrad Haas, mid-16th century, described things like multi-stage rockets, liquid fuel mixtures, get this delta-shaped fins, and even bell-shaped nozzles.
What, bell-shaped nozzles like modern rocket engines use?
Kind of. Concepts way ahead of their time. His work was actually lost and only rediscovered in 1961.
Incredible. Any others?
Johann Schmidlapp was experimenting with staging, actually building 2-stage rockets around 1590. And there's this legendary account, maybe more legend than fact, of Ligari Hassan Chelebi, an Ottoman guy, supposedly making a crude rocket flight in 1633.
A manned rocket flight in 1633. Seriously.
Well, the accounts are debated, but it's part of the folklore. More concretely, you have Kazimierz Siemianowicz. His 1650 book, Great Art of Artillery, became the standard text for like 2 centuries. It detailed multi-stage rockets, delta wing stabilizers, really practical stuff.
And better materials, too.
People were thinking about it. Robert Anderson in 1696 proposed using metal gun barrel type casings, moving away from paper and wood towards something stronger.
Okay, so by the time we get to the 19th century, the foundations are laid, but there's still a big problem, right? Accuracy?
Absolutely. The 19th century is really defined by military use picking up steam, but also this desperate need to make rockets actually hit what they were aimed at.
And this is where Congreve comes back in, building on those Indian designs.
Exactly. William Congreve developed this 32-pound solid fuel rocket. It had a strong iron tube, used the knowledge gained from Mysore, and his demonstrations around 1805 were convincing. They ended up being used quite effectively in the Napoleonic Wars and also the War of 1812 against the U.S.
Ah, and that's the rocket's red glare line from the Star-Spangled Banner, isn't it?
That's it exactly. Those were Congreve rockets being fired by the British at Fort McHenry in 1814 during that war. Francis Scott Key saw them lighting up the night sky.
Wow. Okay, but they were still pretty inaccurate at that point.
Oh, notoriously so. They just veer off course wildly. The standard solution was basically just sticking a really long stick on the side for stability, like a giant bottle rocket.
How long a stick are we talking?
For the biggest Congreve, the 32-pounder carcass model, it had a 15-foot stick attached. Imagine lugging that around.
15 feet. Okay, clearly not ideal. So how did they solve the accuracy problem?
The real breakthrough came in 1844 from William Hale. His idea was genius, really. He modified the rocket's exhaust vents slightly, so the thrust wasn't perfectly straight back. It was slightly angled or vectored.
And that did what? Made it spin?
Exactly. It made the rocket spin along its long axis as it flew, just like a bullet spins because of the rifling in a gun barrel. Gyroscopic stability.
And that meant no more stick.
No more stick, which meant less air resistance, better range, and crucially, much, much better accuracy. Hale's spinning rocket was a huge leap forward.
Were other countries working on this stuff too?
Oh, yes. In Russia, you had Alexander Zasyatko starting serious work on military rockets around 1815. He didn't just build rockets, he built launching platforms to fire salvos of 6 at once. He even formed the first dedicated rocket subunit in the Imperial Russian Army. They saw the tactical potential early on.
And Poland.
Poland, too. Captain Josef Bem experimented with Congreve-type rockets and also developed multiple launchers. So you see this parallel development happening.
Okay, so rockets are becoming serious military tools. But then heading into the 20th century, something shifts again, doesn't it? The dream changes.
It really does.
Yeah.
There's this fundamental pivot. It's not just about warfare anymore. You have science fiction writers like Jules Verne, H.G. Wells capturing the public imagination, and philosophical movements like Russian cosmism that talked about humanity's destiny in space. Suddenly, space travel starts to seem like maybe, just maybe, it's not pure fantasy.
And rockets were the obvious way to get there.
They were the only plausible way, really. And the intellectual groundwork for making that happen was laid by really 3 key figures, giants of rocketry.
Okay, who are we talking about?
First, Konstantin Tsiolkovsky, a Russian high school math teacher. In 1903, he published this seminal work, The Exploration of Cosmic Space by Means of Reaction Devices. He independently worked out the fundamental rocket equation, the math that governs how rockets work, relating velocity change to exhaust velocity and mass ratio. It's called the Tsiolkovsky rocket equation now.
And he advocated for specific fuels.
Yes, liquid hydrogen and liquid oxygen, way ahead of his time in realizing their potential efficiency.
Okay, Tsiolkovsky in Russia. Who else?
Then you have Robert Esnault-Peltry, a Frenchman, around 1912. He also independently derived the rocket equation. Shows how the time was ripe for these ideas. And he even speculated about using atomic power for propulsion. Wildly futuristic thinking.
But the big name, especially in the US, is Goddard, right? Robert Goddard.
Absolutely. Goddard is arguably the father of practical rocketry. Inspired by H.G. Wells as a teenager, he started serious analysis around 1912. He figured out that for solid fuel rockets to be truly useful for high altitudes, let alone space, they needed 3 key things improved.
Okay, what were they?
1, a smaller combustion chamber to build up really high pressure. 2, staging, shedding empty fuel tanks to save weight. And 3, the de Laval nozzle.
Ah, the nozzle again. Explain that a bit more.
So the de Laval nozzle is this specially shaped cone. It narrows, then flares out wide like a bell. This shape takes the hot, high-pressure gas from the combustion chamber and accelerates it as it expands outwards. It dramatically increases the speed of the exhaust gases, which, by Newton's third law, dramatically increases the thrust, the push on the rocket. It makes the rocket way more efficient. Goddard patented these ideas in 1914.
Groundbreaking stuff, but he wasn't exactly celebrated for it at first, was he?
Not at all. He faced a lot of skepticism, even ridicule. There's a really famous or infamous editorial in the New York Times from 1920. It basically mocked Goddard's idea that a rocket could work in the vacuum of space, suggesting he didn't understand basic high school physics, specifically Newton's third law. They thought a rocket needed air to push against.
Oh, wow. Okay, we need to remember that one. The NYT editorial.
Definitely hold on to that thought. Meanwhile, even during World War I, rockets found some niche uses. A French naval officer, Yves Le Prieur, developed these simple air-to-air solid fuel rockets. They weren't very accurate, but they were used to shoot down German observation balloons.
Observation balloons, like Zeppelins.
More like tethered balloons used for spotting artillery. But yeah, taking them down was important. A Belgian ace pilot, Willy Coppens, actually claimed dozens of balloon kills using Leprier rockets.
And Germany was also thinking about space. Oberth.
Yes, Hermann Oberth. In 1923, he published his doctoral thesis, Die Rakete zu den Planetenräumen, the rocket into planetary space. It was actually rejected as a thesis initially, but it laid out more the crucial theory for spaceflight and really inspired a lot of the German rocket pioneers who came after him.
Okay, so the theorists have laid the groundwork. Goddard's starting practical experiments. This brings us right into the modern era, doesn't it, where things really start to take off, literally.
Exactly, and it's an era where the dream of space becomes much more concrete, but it's also deeply and often tragically tangled up with war and military ambitions.
So Goddard keeps working.
He does. And in 1926, near Auburn, Massachusetts, he achieves a major milestone.
Right.
The world's first launch of a liquid-fueled rocket, using gasoline and liquid oxygen. It didn't go very high or very far, but it proved the concept and demonstrated the huge efficiency gains possible with liquid fuels and that de Laval nozzle.
And the Soviets were active too.
Very active. You had groups like the Gas Dynamics Laboratory, GDL, and the Group for the Study of Reactive Motion, GIRD. They eventually merged into RNII, a key research institute. By 1931, they were doing rocket-assisted takeoffs for aircraft strapping rockets onto planes to get them airborne faster. They were also test-firing various ground and air-launched rockets. Some of these actually saw combat against Japan in 1939.
Wow, okay. And then there was that sort of public rocket craze in Germany with cars.
Oh yeah, the late 1920s, that was quite a spectacle.
The car company Opel got involved with rocket pioneers like Max Valier and Fritz von Opel. They held these big public demonstrations of rocket-powered cars, sleds, even rocket-powered gliders. Fritz von Opel himself piloted what's often called the first public manned rocket-powered flight in 1929.
How did that end?
With a pretty hard landing, apparently. That it generated huge public excitement.
And that excitement caught someone else's eye. The military. Exactly. The German military, the Reichswehr, was watching closely. They were banned by the Treaty of Versailles after World War I from developing things like heavy artillery, long-range cannons. But the treaty didn't say anything about rockets. They saw it as a loophole. And that's how they ended up recruiting a brilliant young engineer named Wernher von Braun in 1932.
Braun, who initially just wanted to go to space, right?
That was his dream, yes. He joined the Army program because they had the funding for serious rocket development, hoping it would eventually lead to space travel. The irony, of course, is where it led first.
World War II.
World War II becomes this intense accelerator for rocket tech. On the Soviet side, you had the Katyusha.
The multiple rocket launcher.
Yes. Debuted in 1941. It was kept top secret initially, nicknamed Stalin's organ by the Germans because of its terrifying howling sound and devastating effect. It wasn't very accurate, but firing massive volleys saturated an area. It was relatively cheap to produce, so they made thousands. It definitely had a big impact on the Eastern Front.
But the most technologically advanced and infamous rocket of the war was German.
Without a doubt, the V2. Developed by von Braun's team at Peenemünde on the Baltic coast. Technically, it was called the A4 rocket. During test flights in 1942 and 1943, the A4 actually became the first human-made object to reach outer space, crossing the Kármán line, the recognized boundary.
So the first space vehicle was actually a weapon.
Tragically, yes. It was mass-produced as the V2, which stood for Vergeltungswaffe 2 Vengeance Weapon 2. It was a true ballistic missile. It carried a 1-ton warhead, had a range of about 320 kilometers or 200 miles, and traveled incredibly fast, maybe 4,000 kilometers per hour on impact. There was no defense against it. Once launched, it was coming down somewhere.
And thousands were launched.
Thousands, mostly aimed at cities in Belgium, England, particularly London and France. They killed thousands of civilians, and the human cost of building them was even worse. An estimated 20,000 slave laborers, prisoners from concentration camps, died in the horrific underground factories where the V2s were built.
It didn't change the outcome of the war, though.
Militarily, no. It came too late and wasn't accurate enough to be strategically decisive. But it was a terrifying demonstration of the potential of guided ballistic missiles, a chilling preview of the Cold War.
So the war ends, and then what happens to all this German rocket tech and expertise?
Then begins the scramble. A frantic race between the Americans, the British, and the Soviets to grab as much V2 hardware, documentation, and crucially German scientists and engineers from Peenemünde as they could.
And the U.S. did pretty well out of that.
Arguably the best. Operation Paperclip brought Wernher von Braun and over 100 of his top team members to the United States. They brought their knowledge, even some captured V-2 parts. And the V-2 itself became the direct foundation for the first generation of American large rockets, like the Redstone, which eventually launched the first U.S. satellite and astronaut.
And the Soviets.
They captured V-2s and some lower-level personnel, too. Their program was led by the brilliant Sergei Korolev. They meticulously copied the V-2, calling their version the R-1. But Korolev quickly moved beyond it, developing the R-7 Semyorka. This was the world's first true intercontinental ballistic missile, or ICBM.
Capable of carrying a nuclear warhead across continents.
Exactly, a terrifying prospect. But that same R-7 rocket, slightly modified, is what launched Sputnik 1, the world's first artificial satellite, in 1957.
And the first person in space.
Yuri Gagarin, in 1961, also launched on an R-7 derivative. And here's an amazing fact. The basic design of that R-7 rocket, developed in the 1950s, based indirectly on the V-2, is still used today. The Soyuz rocket that ferries astronauts to the International Space Station is a direct descendant. Incredible longevity.
That's amazing. Now, one huge challenge they had to solve for spaceflight was getting back down, right? Re-entry.
Oh, absolutely. Atmospheric re-entry was a massive hurdle. You're coming back in at incredible speed. Hitting the atmosphere creates immense friction and heat. How do you survive that?
Intuitively, you'd think something sharp and pointy aerodynamic would be best.
That's what many thought initially. But the breakthrough, discovered around 1951, was actually counterintuitive. The most effective shape for a heat shield wasn't sharp, it was blunt.
Blunt? How does that work?
A blunt shape creates a powerful shock wave in front of it as it plows through the air. This detached shock wave actually absorbs and deflects the vast majority, like 99% of the intense heat away from the vehicle, dissipating it into the surrounding air. The heat goes into the air, not into the spacecraft. It was a crucial discovery, kept secret by the military for a while, but it's what made capsules like Mercury, Gemini, Apollo, and Soyuz safe for humans.
So the Cold War is raging, both sides have ICBMs, the space race is on.
And rocket technology just explodes. The 1960s saw incredible progress driven by that superpower competition. Both the US and the Soviet Union poured massive resources into developing bigger, more powerful, more reliable rockets.
Leading to things like the moon landing.
Exactly. Culminating in the US Apollo program and the gigantic Saturn V rocket, still the most powerful rocket ever successfully flown. And this brings us back. Remember that 1920 New York Times editorial that mocked Robert Goddard?
The one saying rockets couldn't work in a vacuum? Yes.
Well, in July 1969, just days after Apollo 11 successfully landed humans on the moon, a feat achieved entirely by rockets operating in a vacuum, the New York Times published a correction.
They actually corrected that old editorial.
They did. It basically said, further investigation and experimentation have confirmed the findings of Isaac Newton. A rocket can function in a vacuum. The Times regrets the error.
Wow. Decades later. That's quite something. Acknowledging Goddard's vindication.
A really powerful symbolic moment, I think.
Yeah.
Connecting that early skepticism to this monumental achievement.
So after Apollo, the U.S. flew 5 more moon landings, then canceled the program in 1975.
Right. The focus shifted to the reusable space shuttle program. Meanwhile, Europe entered the game seriously with its Ariane family of expendable rockets. By the year 2000, the Ariane program had captured a huge chunk of the commercial satellite launch market, showing it wasn't just a two-horse race anymore.
And that brings us more or less up to the present, this new era.
Pretty much. What we've seen really since the early 2010s is another fundamental shift. The rise of privately developed launch systems, companies like SpaceX, Blue Origin, Rocket Lab. The primary driver is shifting again from mainly political and military prestige to increasingly economic incentives. Competition is driving down launch costs dramatically, opening up new possibilities, new capabilities. It's a really dynamic phase right now.
What a journey from, ancient Greek steam pigeons and Chinese fire arrows all the way to Cold War ICBMs and now this private space race. The whole history of rockets is just an incredible testament to human ingenuity, sheer persistence, and maybe, that fundamental curiosity about what's out there.
It really is. And it's a powerful reminder, I think, that inventions we might see as simple at first, like a tube filled with burning powder, can evolve over centuries into technologies that completely reshape warfare, geopolitics, and ultimately our place in the universe.
So, thinking back over everything we've covered, what stands out most to you? Is it those incredibly early Chinese innovations like multi-stage rockets, or maybe the way military needs like the Mysorean Wars or the V-2 directly drove development, or maybe just that New York Times retraction finally happening?
That's a tough question. All those points are fascinating, but perhaps looking forward, the really interesting question this history raises is, with rocket technology still evolving so rapidly, new materials, reusable stages, maybe even new propulsion concepts on the horizon, how are these next steps going to redefine our relationship with space? Are we on the cusp of, truly sustainable off-world living or large-scale resource utilization beyond Earth? How will cheaper, better rockets continue to change life on Earth?
Definitely plenty to think about there. Lots to mull over as you continue your own deep dives. We hope you enjoyed this one, and we'll catch you next time.